That's why those two components are not included in the DC circuits. Whereas in AC circuits, you have a alternating current. This is a AC source. So you will have the circuit comprising of all the components. We are going to discuss that. Okay, so before we start with that, okay, so now, so as usual, DC source is generated by, normally DC source means we try to assume that there is a DC battery. So we'll be connecting that as a source. But as an academician, what we'll do here, we have a setup called, we have equipment called regulated power supply from which we'll take the DC output. There is a um, there is a big machine called generator, which is going to generate the DC voltage, which is going to generate the DC voltage. Same way, there is a AC generator, which is going to generate the AC output. Okay, so now there is a DC generator and AC generator, which are going to generate the output DC and output AC. Okay, so now, so initially, as per the history, they say that in 1800s, people were using only DC supplies, but later on, they found that AC is more efficient. How did they find that? There was almost like the fight between Edison and another scientist, I forgot his name. So there was a big debate between the usage of DC supply and AC supply. Finally, they found that AC is more efficient. AC is more efficient in terms of generation, transmission. Okay, it is not just generating, right? It's AC, whatever may be, let it be a DC supply or AC supply, will be generated in a big plant. If you have heard about the power plants, like a thermal power plant, hydraulic power plant, wind power plant, all these are the sources, right? Okay, so they'll be electricity will be generated there and it will be distributed through the transmission lines to the consumers. The consumers can be like us, household like us, or the industries. They will also be consuming power, right? Okay, so finally they found that AC is more efficient in terms of more efficient and economical in terms of generation and transmission. In terms of generation and transmission, that's the reason people started using AC systems. But now you can see, because of this, what to say, because of this renewable energy sources. Because of this renewable energy sources, a lot of people are, what to say, they have their PV plan, right? They have their PV. Even in VIT campus, there are PV panels are there. We are able to generate the DC. Okay, so now the situation is like always there is some development in the system, right? But still, as a consumer, we are all having only AC supply from the electricity board. Okay, so now, but if you see most of the appliances like your mobile phone, laptop, they all need a DC, small DC source, 6 volt or 10 volt or 12 volt. Okay, so now there is another device called adapter or converter, which is going to convert this AC source into a DC source. Okay, so now we are going to discuss the AC circuits in which the source voltage or the current is a time varying quantity. Okay, so what is this expansion AC? It's an alternating current. What is alternating current? The source, let the source can be voltage or current. It's going to alternate. It's going to vary with respect to time. That's why it is called as time varying source. The source is going to be a time varying one. So here you can consider this is a time varying source. This is also a time varying source. This is also a time varying source. All these are periodical waveforms, but this is also time varying, but this is non-periodical. Okay, so now here our interest is, or in this particular module, we are going to study sinusoidally time varying excitation as a source. That is sinusoidal signal as a source we are going to consider for this module. That is for this, to discuss this AC circuits. Okay, so now why sinusoidal signal? Okay, why sinusoidal signal? Okay, so there are a lot of advantages There are a lot of advantages, or there are many reasons why people are going for sinusoidal signal. Okay, so now here, so sinusoidal signal means mathematically it can be a sine or cosine function. Mathematically it can be a sine or cosine function. Okay, so circuits driven by these sinusoidal signal, they are called as AC circuits. Okay, now let's see what are the advantages, what are the different reasons why people are using sinusoids. Okay, first and foremost reason is almost in nature, most of the signals are characteristically sinusoidal in nature. Okay, examples like pendulum or vibration of a string. Probably in your physics you might have studied, no? So pendulum, which is going to move. Okay, so that is, you will have a sinusoidal signal. And then vibration of a string and ripples on the ocean. Okay, so that is one thing. Second thing is sinusoidal signals are easy to generate. They are all easy to generate and transmit. Okay, that is one reason. Then if you take any practical periodical signal, when you go for analysis of all those periodical signals, easily using Fourier series, those periodical signals can be represented by a sum of or a function of sines and cosines. So it will be easy to analyze. That's also one of the reason why sinusoidal signal is preferred for the AC circuits. And then the last reason is, if you take, compared to any other signals, mathematically, if you take the sine function, the derivative and integral of this sine function is again sine only. Sine and cosine both are same only, no? So derivative and integral is also same sign. Okay, so due to all these reasons only, AC circuits are generally analyzed by considering sinusoidal signal as a source. By considering sinusoidal signal as a source. Okay. Now, okay, so you all might have come across this. This is the sinusoidal signal. This is the sinusoidal signal. Okay, so here both the signals are represented with different arguments. This is with omega t and this is with t. Or I can say that this x-axis argument is represented in terms of anybody? We have two units, no? That is here. This is magnitude of a signal. This is a time varying signal. So definitely magnitude of a signal, and the x-axis is a time period. Okay, how your signal is varying with respect to time. Okay, so now this x-axis can be a time period. This can also be represented by using this omega t argument. Okay, we'll see what is this, what is that phase angle. That is omega t is nothing but angular frequency, no? So we'll see that. Okay, so now generally this sinusoidal signal can be represented by an equation called V of t. Why we write it? Normally in DC circuit, simply we write V, no? But here, why do we write V of t? Because it's a time varying function. The function is represented by means of function of t. Okay, so Vm sine omega t. Vm sine omega t. Okay, so what is Vm? Vm is the amplitude of the signal. Vm is the amplitude or magnitude of the sinusoidal signal, and omega is the angular frequency. Omega is the angular frequency. So when I say x-axis is omega t, it is angular frequency. So angular frequency, the unit is radians per second. Okay, radians per second. Okay, so now here the same x-axis can also be represented by the time period. So here the unit will be seconds. Here the unit will be seconds. The same thing, this angular frequency can also be written in terms of theta in degrees. Okay, angular frequency, that is your x-axis, can also be represented by means of, that is, we can write Vm sine theta also. Here theta is nothing but omega t. Theta is nothing but omega t. Okay, so here this is now angular frequency. This is in radians, whereas this is in degrees. This is in degrees. Okay, so now here, what is this capital T? What is this capital T, or what is this omega t? Okay, that is nothing but a period of a signal. Okay, this is a periodic signal. What is meant by periodic signal? The signal is going to repeat for every t seconds. The signal is going to repeat for every t seconds. Okay, repeat itself for every t seconds. So now what is this t? T is a time period. After a time period 1t, the signal repeats. Again, after 2t, the same signal repeats. Okay, so now here, based on this comparison, the time period capital T, that is, this is T and this is omega T. So now when you compare these two, when T is equal to T, that is 1 cycle. Similarly, here when T is equal to omega T, that is 1 cycle. Okay, so from this, we can find that capital T is equal to 2 pi by omega. Capital time period is equal to 2 pi by omega. Okay, so this is your sinusoidal signal. So here the interesting parameters are, one is the amplitude of the signal, the other one is the angular frequency, your omega T. That can be either in radians per second, or it can also be represented in degrees. Okay, so what is the relation between this time period in seconds and angular frequency in radians per second? This is the relation. Okay, what are all the other important parameters for a sinusoidal signal? Okay, so now when you take a DC voltage or a voltage source of a DC circuit, simply it's a DC value. We'll say 10 volt or 20 volt or 5 volt or 7 volt. Whereas here, using what parameter, we'll try to represent the voltage source, whether we'll say it as a mathematical equation 5 sine omega t, or we'll say with the maximum value. Okay, so now we have different ways of representing the sinusoidal voltage signal. It can be a voltage or current signal, but we can represent this voltage in different forms, in different ways. Okay, so what are all those things? One is instantaneous value. One is instantaneous value. So this is going to be a time varying signal at different instance. For example, at t is equal to t1, a time period t is equal to t1, what is the voltage? So that is the instantaneous value. It can be at t is equal to t2, what is the voltage? So these are all the instantaneous values of a voltage signal. Okay, the same. So in E of t, it can be represented with E of t. Okay, and then second, you can represent the voltage with peak value also. What is a peak value? Peak value is the maximum value. Peak value is the maximum value of the signal, maximum value of a sinusoidal signal. Okay, as measured from zero. From zero, what is the maximum value? Okay, and then peak to peak value. So this is a sinusoidal signal, which is a periodical signal. So now this is going to alternate between positive peak and negative peak. Okay, it's going to be a positive peak and negative peak. Okay, periodical signal, the signal is going to repeat itself for every time period t. Okay, again here in periodical signal itself, you have again two different things. One is symmetric signal, the other one is asymmetrical signal. The difference between a symmetrical and asymmetrical is, in symmetrical signal, you will have the symmetricity, that is your positive maximum and negative maximum is same. Whereas an asymmetrical signal, you can have two different peak values. Just for example, I'll show you. This is asymmetrical signal. Okay, so when you, with respect to the zero level, with respect to the origin, so your positive and negative is not symmetrical. But this is periodical. Because after every t, the signal repeats. But the thing is, see, with respect to zero level, if you compare, your positive and negative is symmetrical. So this is a symmetrical signal. Whereas here, when you compare with respect to zero, when you compare your positive and negative side, it's not symmetrical. Okay, so now with respect to symmetrical signal, peak to peak is, you have your Vm as the maximum peak value, maximum peak voltage. Similarly, the same negative value is also available. Now peak to peak is nothing but 2 Vm. Peak to peak is nothing but 2 Vm, or this is generally represented with the notation VPP, voltage, peak to peak voltage. Okay, or EMF. Okay, generally the voltage can be represented as either EMF or voltage. No, so now periodic waveform, as discussed already, it's going to continuously repeat itself after the same time interval. Okay, so now here cycle. What is meant by cycle? Okay, So the portion of the waveform which is going to repeat, no, the portion of the waveform or signal is going to repeat itself. Okay, so the portion of the waveform for one period of time. For example, after every t, it's going to repeat. So what is the portion of waveform for this one t, for this one time period? Okay, it's nothing but cycle. Okay, it's nothing but cycle. See here, I can say the cycle as either this complete can be called a cycle, or you start from this positive maximum and end with another positive maximum. This is one cycle. The same way I can say this is also one cycle. This is also one cycle. See, similarly here, this is also one cycle. Okay, after this, it's going to continue, right? So you can call either this as one cycle or this complete waveform. All these are one cycle. Okay, now frequency. Okay, so now number of cycles that occurs in 1 second. Number of cycles that occur in 1 second is nothing but a frequency. Okay, for example, let us consider 3 different waveforms. See here, only 1 cycle per second. So the frequency is 1. The frequency is 1. Okay, see here in what is frequency? The number of cycles that occurs in 1 second. So here, as per this given waveform, only 1 cycle in 1 second. So the frequency is 1. Okay, whereas here in 1 second, how many cycles we have? We have how many cycles we have? We have 2 cycles. This is 1 cycle and we have another cycle. Okay, sorry, not 2 cycle, 2.5 cycles. In this, we have 2.5 cycles. So what is the frequency here? What is the frequency here? 2.5 cycles per second. 2.5 cycles per second. Whereas here, when you consider here, we have the frequency would be 2 cycles per second. The frequency would be 2 cycles per second. So this way, I can represent the frequency of a sinusoidal waveform. So now when you compare this time period and frequency, because we are saying per second, no? We are saying that frequency is per second, right? So now I can say that frequency is inversely proportional to the time period, or I can say that F is equal to 1 by T hertz. The unit of the frequency is cycles per second or hertz. The unit of the frequency is cycles per second or hertz. Okay, so with respect to y-axis, the voltage or current can be represented with the instantaneous value, peak to peak, or these 3 are the values. Other than that, we have 2 more representations like average value and RMS value. We'll see to that. And then with respect to x-axis, we can say the cycle or the time period or frequency. Okay, the frequency can be normal frequency or angular frequency. When you convert from the time period, that is called frequency. Okay, so now when you convert from the argument omega t, that's called angular frequency. Okay, so now here, now this is a periodical signal, right? This is a periodical signal. So the waveform, to justify how we say that this is a periodical signal, see here, V of t plus t. T is one time period. T is one time period. Okay, so V of t is Vm sin omega t, or V of t is Vm sin omega t. Okay, now let me see what is the value of the voltage after one time period or one cycle t. Okay, so now let's apply the same thing on the right hand side also, t plus t. Okay, now as per this, Vm sin omega t plus t is equal to Vm sin omega into t plus, this can be, that is your time can be in angular frequency, can represent it as 2 pi by omega. 2 pi by omega. So now Vm into sin omega t plus 2 pi. Okay, that is when you bring it inside. When you bring it inside, this becomes omega t, and this omega and omega gets cancelled, and you have 2 pi. Okay, so what is 2 pi plus omega t? We know that sine of 360 plus anything, 360 plus anything that comes in the first quadrant. So that can be Vm sin omega t. So now when you consider V of t and V of t plus t, we have the same thing. So we can say that this is a periodical signal. That is V of t repeats itself after every t seconds. Okay, now Vm sin omega t plus phi. Vm sin omega t plus phi. What is this phi? Omega t is the x-axis argument. What is this phi? Okay, so always we say that this is the reference sinusoidal signal which starts from 0, goes to the maximum peak, and then come back to 0, and then go to the negative peak, come back to 0, then continue. Okay, so now here whether this sinusoidal signal is going to start from the origin or start before the origin or start after the origin is represented by the term called phase. What is the phase difference? What is the phase difference? Okay, so that is nothing but phase. Okay, so generally for this sinusoidal signal, since it's starting from the origin, Vm sin omega t plus 0. There is no phasor difference because it's starting from the origin. Okay, whereas when you consider this dotted sinusoidal signal, we can call it as, we can write the mathematical representation of this sinusoidal signal as Vm sin omega t plus phi. Why do we write it as plus phi? Because the signal starts before the 0 itself. Okay, so now what is this? How much difference? How much phasor difference? It's nothing but phi. It's nothing but phi. Okay, so that's way. See, suppose if you have a sinusoidal signal like this, if you have a sinusoidal signal like this, okay, so now what's happening with respect to the reference? With respect to the reference, it's starting later. The origin of this signal, let us consider this is V2 or V3. Already we have V2, no? So let us consider this is V3. So V3 starts after reference signal V1. V1 is my sinusoidal reference signal. Okay, so now V2 starts before V1, whereas V3 starts after V1. How do I say it's after V1? Because my 0 signal, when with respect to origin only, we will compare. Okay, so now this is the phase difference. So now how do we represent this phasor quantity? V3 will be Vm. Anybody? Vm sin omega t minus phi. Okay, so this plus phi is nothing but leading. This plus phi is nothing but leading. V2 starts before V1. V2 leads V1 by an angle called phi. Similarly, when I say minus phi, it's nothing but later. V3 starts later. So V3 is lagging behind V1 by an phase angle of phi. Okay, so that way we can have the sinusoidal signals like this also. It's not that always my sinusoidal signal will be like this. You can have sinusoidal source like this also. So how do we represent mathematically? With the phasor difference, phi. Okay, so now the phasors. Now this is my sinusoidal signal. So mathematically we can have the equation like this. The phasors, that is we write Vm sin omega t plus phi, Vm sin omega t minus phi, right? So now the phasors can be represented. That is the sinusoidal signal can be represented by using phasors also. By using this phasors also. What is this phasors? That is, I have my sinusoidal signal mathematically written as, sorry, 1 minute, yeah. I have my sinusoidal, yeah. I have my sinusoidal signal represented mathematically as Vm sin omega t plus phi or minus phi, whatever. Okay, so now this sinusoidal signal can be represented by a phasor. What is a phasor? Phasor is nothing but a complex number which represents the amplitude and phase of the sinusoidal signal. For example, if I have my sinusoidal signal mathematically written like this, then the phasor equivalent of this, will be magnitude and phase angle, right? So we can write Vm. Okay. So now the phasor quantity, the phasor representation of the sinusoidal signal can be rectangular form, polar form, or exponential form. So when I write it in the rectangular form, it is x plus jy. When I write it in the rectangular form, it is x plus jy. Okay, when I write it in the polar form, r phi. Okay, when I write it in the exponential form, r into e power j phi. So now what is this r? R is nothing but magnitude of the signal. What is phi? Phi is nothing but phasor quantity. Okay, whether it is whether it is aligned with the reference signal, whether the phi is 0, or whether it is leading the reference signal plus phi, or lagging the reference signal minus phi. Okay, so r is a magnitude and phi is the phasor difference. And now the complex form. Probably have you studied this complex numbers? Multiplication of complex number, addition of a complex number, vector quantity.
Yes, ma'am.
Okay, so normally you might have studied this vector quantity, right? Same thing. So the complex number. So now here the conversion between these two. Okay, the conversion between these two. If I have a polar form complex number, how do we convert it into a rectangular form? So now if I have it in rectangular form, how do we convert it into the polar form? So the equations are given here. Okay, so r is equal to square root of real value plus imaginary real value square plus imaginary value square. So now the phase angle is tan inverse of y by x. Similarly, if I have this polar form, how do we convert it into rectangle? R cos phi and R sin phi. Okay, so now how can I write this sinusoidal signal in phasor form? Okay, so now this sinusoidal signal, see here my sinusoidal signal is starting from the origin. My sinusoidal signal is starting from the origin. So now here the magnitude is 0 and the phasor is also 0. The magnitude is 0 and the phasor is also 0. Now here, see, this is my sinusoidal signal at this moment. At this moment. Okay, so now what is this? This is the magnitude. This is the magnitude and the phase angle is 45 degree. Okay. Again, my sinusoidal signal. If this is the origin, then this is the magnitude and this is the phasor angle. Okay, so next position. So my sinusoidal signal is like this. So we can easily represent the sinusoidal signal in complex plane. We can easily represent the sinusoidal signal in complex plane. So this is complex plane, no? So x-axis is a real value, y-axis is imaginary value. So the sinusoidal signal starts from 0, then 45, 90, 135, 180, so that way. So my sinusoidal signal is going to be, can be represented using a complex number. Okay, so this is my 0 signal, this is my positive peak, and this is my negative peak. Okay, at what angle we have a negative peak? Sorry, this is my negative peak. Okay, and then we have. Okay, so this way I can, so this is the we can have a sinusoidal signal. We can represent the sinusoidal signal in a complex plane. So the sinusoidal signal can also be written in the complex form, can also be represented using a phasor. Why? Because the sinusoidal signal can be drawn in a complex plane. So this can also be represented using a phasor. Okay, now AC waveforms and average value. Okay, so before I start that, for example, I will give you one simple example. So let me see whether you are able to. Now, so now, okay, so now I draw a sinusoidal signal. Okay, so this is my sinusoidal signal, that is V1. Somehow I'm not very good in drawing this, especially using this digital pen. Okay. Okay, so now this is T. Okay, and this value is 5. This is 80 degree. Okay, so can anyone tell me V1 of t using a mathematical form. And can anyone tell me this V1 in polar, that is in phasor? This is my given sinusoidal signal. This is my given sinusoidal signal. Can anyone tell me this? How do I represent this sinusoidal signal? Using a mathematical sign form representation and using a phasor form representation, which is easy to say here. So the standard representation is Vm sine omega t plus phi. Okay, so now plus or minus phi. Okay, so now Vm is nothing but the maximum value, okay, or the magnitude of the sinusoidal signal. So here the magnitude of the sinusoidal signal is given as 5. Okay, 5 sine, and then the standard reference sinusoidal signal starts from the origin, whereas this signal starts before the reference signal with the phase difference of 80 degree. So I could say that Vm sine omega t plus 80 degree. So this is the representation of a signal V1. Okay, so this is the sinusoidal representation. Now when I try to represent this in the phasor form, you will have, if I write it in polar form, R is the magnitude and phase angle is 80 degree. Okay, if I want to write it in the rectangular form, then that is V cos 80 degree plus J into V sine 80 degree. Right? Yes, R cos phi and R sine phi. Okay, what is R here? R is nothing but the magnitude. Okay, so please remember, when you have the AC circuit, when we are going to discuss this analysis of AC circuits, we can have the representation of a source. Source will be an AC source, right? Sinusoidal source, right? So the source can be given either by means of a sine function or by means of a phasor value. The phasor value can be given either in polar form or in the rectangular form. Okay, so whatever may be the case, I should be able to continue with the analysis. Okay, so is this clear? Any doubt here?
Ma'am, what does J stand for?
J is the, yeah, that's what, the complex plane I was telling you, no, that is the number. So probably you might have studied the number with real value only, Okay, so you have a complex number representation wherein you will have real as well as complex value, complex value. So this is the imaginary plane. So this is my complex plane representation. So my x-axis is a real value and y-axis is an imaginary value, imaginary axis. Okay, so this imaginary axis is represented with the J complex number, J. That is, for example, if I have the value like this, okay, then I can represent with A plus JB. Okay, so this is my complex plane. I have my x-axis is a real value, y-axis is an imaginary value. Okay, so now this J, whatever is coming along with J, no, that is nothing but the imaginary value. For example, when you consider this sinusoidal signal, at t is equal to 0, or when omega t is equal to 0, what is the value of this sinusoidal function?
5 sine 80 degree.
Sine 80 degree, you will have some value. 5 into sine 80 degree will be the value, right? So where will it come? It will come here only. Okay, so now when you try to represent like this, you, for example, all these things.
Replace J by I.
Sorry?
Can we replace J by I?
Yeah, correct. Oh, probably that's new. Okay, I, yes, I is a complex value. Okay, so we can write A, I or J. Okay, so I thought you have studied this in your mathematics. Okay, So now for AC source, we discussed AC circuits going to have sinusoidal signal as a source value. Now the source, AC source, can be represented either in the sine form or in the complex form. Okay, that's what I'm trying to say here. Okay, so now the sinusoidal signal, as discussed already. So now the sinusoidal signal can be represented either with the peak value or instantaneous value. Now we have two more representations of this voltage signal. One is the average value, the other one is the RMS value. One is the average value, the other one is the effective value or RMS value. Okay. So generally we prefer to have the voltage with some value, right, with some constant value. We have a representation. Okay, so now how do I represent a constant value for a AC source? Okay, how do I say a constant value for a AC source? Okay, one thing is either we can represent an average value, since it's a time varying signal. So we'll have either when I want to represent the sinusoid time varying signal as a constant value, we can represent either by using an average value representation or by using RMS value representation. Okay, so now here, in AC quantities, we have frequency, time period, instant value, peak to peak value, everything is there. Okay, so now how in DC we say 12 volts, no? Similarly, if I want to say AC quantity with a constant value, AC quantities. Okay, so now we have an option to specify an AC signal by its average value. Okay, so now how do I determine the average value? How do I determine the average value for a given sinusoidal signal? Okay, so it's not that sinusoidal signal, you can have any periodical signal. So now this average value, this procedure can be applied for any periodical signal, Okay, so generally we know that how do I determine the average value? For example, when I want to find the average marks of a class, then I will sum all the marks, then divided by the number of students. Okay, I will sum or I will add the marks of the individual students and then divided by the number of students. That will give the average marks, right? Similarly, that's a normal mathematical. So here it's a waveform. So now how do I find the average value? For example, if I have a signal like this, if it is a repeating signal, then I take the discrete values at different instance, then sum all these values and take the total number of students. No, similarly here, this is my signal, right? So sum all the values and take this base value as a reference. Okay, so now divided by the base value will give us the average, right? So now here for the waveforms, we don't know the discrete values. At different time instance. So what is the general procedure? What do we do? Here we consider this area of a uniform waveform, area of a periodical signal. Okay, we will consider the area under the curve. Okay, we will consider the area of this waveform because it's a periodical signal. After that, it's going to repeat. No, area of this, and this. Okay, so that will be the total area divided by the base value. What is the time period? That will give the average value of the periodical waveform. Let me repeat. So here AC signal, how we have a DC, I say 12 volt battery, 15 volt battery, something like that. No, similarly, when I want to represent a AC signal also with some constant value, we have two ways to represent it. One is by using its average value representation or by using a RMS value representation Okay, now how do I determine the average value for a given sinusoidal signal? Okay, so generally we know that average means sum of the total number divided by the, for example, when I want to find the average marks of the classroom, then add all the marks of the students, then divided by the number of students. Whereas here, this is a waveform. So we don't know the discrete values at different instance. So what is the procedure? What we can do here? Find the area. Find the area of this waveform. Then divided by the time period. Divided by this base value or time period. Will give us the average value of this waveform. Will give us the average value of this waveform. So now, how do we determine the area of the curve? Area under a curve can be anybody in mathematics you might have studied, no? What is the meaning of this integral of any mathematical function of any waveform? Area under the curve can be determined by integrating. Area under the curve can be determined by integrating
Small
the
parts,
function.
small.
Yes. Okay. So now here also for the given waveform, we have the mathematical function, integrate this. So that will give us the area. That will give us the area. Okay. So now, for example, here one more challenging part here is this is a sinusoidal signal. So we know that the signal is going to repeat and signal will have positive as well as negative portion. Okay. Now when I consider the area under the curve for a positive period and for a negative period, and then when I try to sum, what will happen? Both will get cancelled and we'll get the average value as 0. We'll get the average value as 0 for any sinusoidal signal. For this sinusoidal signal or for this sinusoidal signal, since it's a periodical signal and symmetrical signal, if I try to find the average divided by the base or time period, then what will happen? The average value will end up with giving a 0 because area under the curve for the positive portion and negative portion will be equal. When I try to sum up, it will become 0. So generally for the sinusoidal signal, what is that we will do? We'll consider either half cycle or we will try to consider only half cycle. We'll consider half cycle. That is, consider like this, or we'll consider a signal like this. Okay. Yes, somebody was interrupting me. Oh, time up. Okay,
Yes.
we'll continue. Yes, sorry, we will continue. One more important announcement I forgot to mention here. 1 minute, I'll just download the attendance. Those are having a class can leave so that. Yes, tomorrow's lab. No? So tomorrow we have lab, right? 3:50 to 5:30. So I have some other engagement during that time. So we'll slightly shift the lab schedule. Shall we make it from 2:30 to 4 p.m.? I have checked your timetable. All of you are free during that time. So shall we have the lab schedule from 2:30 to 4 or 3 to 4:30?
2:30 to 4, ma'am.
2:30 to 4.
Okay, good. So 2:30 to 4 we will plan. Okay. So all of you please note it down. So tomorrow's lab only for tomorrow. The lab is from 2:30 to 4. Instead of 3:50 to 5:30, we will have the lab session from 2:30 to 4. All of you please join by 2:30. Only for my slot, not for the other part of the students. Yes, the other students, you have registered with Febin sir, no? Not for Febin sir students, only for my students. Only for tomorrow, my lab slot, it's from 2:30 to 4. Okay, so those who are having a class, please, you can proceed. Others, if you have any.
Can you just give a clear view about our portions, ma'am?
That's what my first unit completely. What is that we have discussed in the first unit? We started with the DC circuits, what is current, voltage, charge, all those things. Then we discussed Kirchhoff's law. We started with Ohm's law and Kirchhoff's law, series circuits, series parallel combination. What else? That's all right. Then after that, we discussed different methods like source transformation, mesh analysis, nodal analysis, and then for real-time applications, these theorems will be suitable. So we discussed maximum power transfer theorem. For maximum power transfer theorem, for the sake of solving maximum power, we discussed Thevenin's theorem also. So all these are for module 1.
Ma'am, we don't
Module
have
2.
Norton's theorem, right?
No.
Okay,
You don't
thank
have
you.
Norton. Okay, so for module 2, I'm starting now. Probably by next class, we'll discuss the continuation of this average value, RMS value, peak factor, and one more form factor is there. Then we will see a simple R alone, AC supply with R, AC supply with L, and AC supply with C. Okay, how much ever we could discuss, we will see on Friday. So till that much, you can prepare for your CAT 1. Okay.
Ma'am, sorry to disturb, ma'am. Actually, I'll be traveling tomorrow, ma'am. So I will try to join as soon as possible, but will it be okay if I join like 15 minutes late for the class, ma'am?
Okay, no problem.
Thank you. Thank you.
Okay, ma'am. Okay.
Thank you, ma'am.
Okay, ma'am. See you tomorrow.
Ma'am,
Hmm.
actually, I was not able to submit the assignment in time because the
Yeah, I have mentioned already, no? Just after your CAT 1, I will create one more link. Those who have pending, maybe they all can submit in that link, common link. After CAT 1, I will give one common link for the pending students. For the students, those who couldn't submit due to some valid reasons, can submit in that link. So don't worry, I will give it after CAT 1 so that you can submit this experiment.
Okay,
Ma'am?
ma'am. Thank you.
So our CAT syllabus, both module 1 and module 2 now, ma'am, total.
Module 2 only one or two topics, ma'am. So that is till Friday. Today we started with the basic sign introduction. Then probably on Friday we'll have some more. So
IMS, ma'am.
yeah, RMS, average value, and then we'll start with simple R and L circuit, or simple R and C circuit.
Single R. Okay, ma'am.
Okay.
A small doubt, ma'am. In the polar form, actually, the Z is equal to R into theta, it was there, ma'am. So if that 80, that is that theta, ma'am, if it is before the y-axis, then we write R into 80, ma'am. But if it is axis, should we write R into minus 80, ma'am?
Exactly. So we'll write phi itself as minus 80. R angle minus 80. So that cos of minus 80 and sine of minus 80 will be there.
Yes, ma'am.
Okay.